Hello everyone and welcome to video number 3 in the three-phase circuits course. In this video we are going to cover three-phase configurations, star and delta connections. Let's start. As I mentioned, we have two configurations, either star connection or delta connection. So some textbooks write star or W-Y-E-Y or the English letter Y. In delta connection, they write mesh or delta, a Greek letter. So for star connection, we have 3 or 4 wires, and it's important feature here that the neutral is accessible. But for delta connection, we have only 3 wires, neutral is not accessible. So for star connection, as you can see here, we have 3 loads. I presume now that we have balanced loads, so we have phases A, B, C, and the neutral point N. So we can have 4 wires, and if the system is balanced, we can ignore the neutral, so we have 3 wires in this case. But the neutral point is accessible, so we have a potential can be measured at point N. So either you connect the circuit like what we can see here, or maybe like Y English, or you can connect that one like the motor nameplates showing to you 3 coils, so you are going to have ABC and the neutral point here. Regarding the delta connection, as we can see here, we have 3 terminals, we have no neutral, so the loads are connected as a triangular shape, so the current is circulating here inside this delta connection. If we have it like 3 impedance, so we have phase A, phase B, phase C, so the start of the phase A is connected to the finish of B, start connected to finish, start connected to finish. Or the vice versa, we have finish connected to start, finish connected to start, and finish connected to start. Any difference? If we're going to connect that one to a static or dynamic load, might be there is no difference. But if we have a transformer, it will make a difference. So you need to consider that one, because that one is going to change the phase group. Transformer and grouping of the transformer will be another course, so this is not our target now. But now we have star connection or delta connection. How to connect the star? You have 3 phases connected to the 3 loads, and we have one common point is neutral point. For delta connection, you need to connect the coils as a start to finish or finish to start, and then you are going to connect to the 3 terminals ABC, the supply. If you'd like to know more about how to connect the star or delta practically, please visit the video Induction Machine course, chapter 2, video number 2, Induction Machine Terminals and Slip Speed Concept. So in this video explained practically how to connect the machine as a star or delta. So now we are going to look for star and delta connections as a source. So we are going to start 3-phase sources. We are going to start by star connection. If we have 3 sources, so each source has 2 terminals, for example, A dash, B dash, C dash. So we have this sequence, as you know, ABC sequence. If you like to know more about labeling, please return back to 3-phase induction motor course, chapter 2, video number 2. If we connect A dash and B dash and C dash together, we have a neutral point. And in this case, we have 4 wires. But if we are going to have a balanced system, we can ignore the 4th wire and we have 3 wires. But if you notice here, we have A, B, C will be connected to the load. So this source is VN is going to generate a current IA in the phase, and this current will be the same because they are connected in series here, IA in the line. So it's the first time to hear this word. We have line. So we have 3 lines here, A, B, C. So we have a voltage between A and N point. So that one is V and angle 0. And VBN equals V angle minus 120. VCN, V angle plus 120. So we can write that one as VA, VB, VC. If the neutral point has 0 potential, because we know that Vn equals Va minus Vn. And if that one is 0, we can write it as Va. If you notice here, we have the phasor Va, Vb, Vc, they are shifted 120 degrees. What is the voltage between A and B point? So we have a new voltage here is called VAB. And that one is a line voltage. Some textbooks write it as line voltage, line to line voltage, or phase to phase voltage. All of those are the same. But only phase voltage is VAN or VA or VB or VC. But line to line or phase to phase or line, they are VAB or VBC or VCA. So VAB equals VA minus VB, and those are phasors. So how we are going to find the relation between VAB and VA or VB? We notice that the potential or the voltage value here for phase voltage is V and angle 0 for phase A. So if we look for that one as a phasor, we have VAN and VBN. So to have VA minus VB, we are going to reverse this phasor here. So that one is minus VBN. And we are going to have the vectorial sum. So that one represents VAB, the green line. So this angle is 180 degrees. That one is 20 degrees. So this line is going to halve this angle. So we have here 30 degrees. So how we are going to find the relation between VAB and VAN? So we are going to project the line here, make that one is 90 degrees, so that one is going to have this line. So we have a right triangle here. So in this case, for this triangle, for example, we have the voltage V represents the hypotenuse, and this part represents the adjacent, and that one is the opposite. So what is the relation between this line, the black one, and the green one here? So that one is cosine 30, root 3 over 2. But VAB is double this value, so VAB equals root 3 over 2 multiplied by 2 will be root 3V. So what is the relation now between line voltage and phase voltage? In magnitude, root 3, but with the angle shifted by 30 degrees. So let's look here. So that one represents root 3V, and the angle is 30 degrees, leading by 30 degrees. So the line voltage leads the phase voltage by 30 degrees, and the value for the line voltage is root 3, the phase voltage. So now we can write the relation between phase voltages and line voltages. So phase voltage is V angle 0, V angle minus 120, V angle plus 120. That one is VC. So for line voltages or phase-to-phase voltages or line-to-line voltages, VAB equals root 3V angle 30. VBC equals root 3V angle minus 90. From where minus 90? Minus 120 plus 30 degrees. And VCA equals root 3 angle 150. So from where 150? 120 plus 30 degrees. So the line voltage leads the phase voltage by 30 degrees and equals root 3 the value. What about the delta connection? For the delta connection, we have three sources. They are connected as a triangle. If you remember, each source consists of two terminals, start connected to finish. So we have three voltages here, VAB, VBC, VCA. There is no neutral point. So in this case, VAB equals V angle 0, VBC equals V angle minus 120, VCA equals V plus 120. So the voltage between these 2 points is the voltage between these 2 points. Now, if you notice here, there is a current out of the source and there's a node here. So Kirchhoff current law can be applied here, where I capital A, the line current, which is different rather than the phase current, so can be calculated using Kirchhoff current law, where IA equals IA minus I. So for the phasor diagram, we are going to assume that the current is lagging the voltage by angle theta to solve this problem. So we have VAB, VBC, VCA, they are shifted 120 degrees, and definitely the current IA, IB, I small c as well, they are shifted 120 degrees. But the current is shifted from the voltage by angle theta. So we can write the currents as IA equals I angle theta, IB will be angle theta minus 120 for the same amplitude, and IC with the same amplitude but theta plus 120. So what about the line current? This is a question. We're going to apply the same concept we did for the star, but for the current in this case. So we have IA minus IC, so the reverse of IC will be in this direction. We are going to have I capital A in this case. So that one will be root 3I, but lagging the phase current by 30 degrees. So that one is opposite to the star connection. Star connection, the voltage is leading. Here the current is lagging. So how we are going to write the current? Now, line currents equals root 3I angle theta minus 30 degrees. IB equals root 3I angle theta minus 120 minus 30 degrees. And IC equals root 3I angle theta plus 120 minus 30 degrees. So let's conclude that one. The line current in delta connection equals root 3, the phase current, and shifted by 30 degrees, where the line current lags the phase current by 30 degrees. And the phase voltage equals line voltage in this case. What will I watch in video number 4? In video number 4, we are going to cover 3-phase circuits, star load. See you in the next video.